Hi everyone, my name is Daifeng Liang. My presentation is titled Brain Tumor Detection and Segmentation Using Deep Learning. This is one of my most ambitious data science projects I did for my master's degree in data science at Harvard University, where I explored both classification and semantic segmentation of brain MRI images using modern convolutional neural network architectures. My project combines multiple families of deep learning models, including VGG, ResNet, EfficientNet, and ConvNeXt for tumor detection, as well as SAM-assisted segmentation, UNet, and DeepLab V3+ for precise tumor localization. My motivation behind this work is to build an end-to-end computer vision pipeline that reflects real-world clinical workflows. First, determining whether a tumor is present, and then accurately delineating its boundaries. Throughout this presentation, I walk through the dataset, preprocessing strategies, model architectures, training and evaluation methods, comparative results, and lessons learned. My project was developed as part of my coursework in the CSCI E-25 course, Computer Vision, and it reflects both applied deep learning practice and experimental model comparison. Brain tumors are among the most critical neurological conditions, and their diagnosis often relies on manual interpretation of MRI scans by radiologists. While expert interpretation is highly valuable, it is also time-intensive, subjective, and sensitive to inter-observer variability. In clinical settings with heavy workloads, this limitation can impact diagnostic consistency and speed. From a machine learning perspective, this creates a strong opportunity for automated decision support systems that assist clinicians rather than replace them. The core problem addressed in this project is twofold. First, can we reliably detect whether a brain tumor exists in an MRI image? And second, once detected, can we accurately segment the tumor region to provide interpretable spatial information? These two tasks mirror real diagnostics workflows and introduce different modeling challenges. Classification focuses on global image features, while segmentation requires pixel-level precision. My motivation for this project is to evaluate how modern deep learning architectures perform on both tasks under realistic constraints, such as limited data and image variability. The dataset used in my project consists of brain MRI images sourced from a publicly available KGO focused on tumor detection. It contains images labeled as either tumor positive or tumor negative, with a total sample size slightly above a few hundred images. While this is relatively small for deep learning, it reflects a realistic scenario often encountered in medical imaging. The images vary in resolution, contrast, and tumor appearance, including differences in size, shape, and intensity. Some images even contain clearly defined tumors, while others exhibit more subtle abnormalities. An important characteristic of this dataset is class imbalance, with slightly more tumor-positive images than negative ones. This imbalance influences model evaluation and requires careful interpretation of accuracy metrics. The dataset primarily consists of 2D and MRI slices. Rather than full 3D volumes, which guided the choice of model architecture toward 2D convolutional networks. Overall, the dataset provides a challenging but practical testbed for evaluating classification and segmentation performance under constrained conditions. Preprocessing plays a crucial role in medical image analysis, especially when working with small dataset. In this project, Multiple preprocessing steps were applied to enhance tumor visibility and reduce irrelevant background information. These steps include contrast enhancement, noise reduction, and spatial normalization. Another key technique used is multi-curve, multi-scale image contrast amplification, which enhances local contrast across multiple spatial scales. This helps highlight tumor regions that may otherwise blend into surrounding tissue. In addition, morphological operations in cropping were applied to reduce background artifacts such as skull boundaries and empty image regions. To improve generalization and reduce overfitting, extensive data augmentation was used during training, including rotations, flips, brightness adjustment, and zoom transformation. These preprocessing steps significantly improved training stability and helped the model focus on medically relevant features rather than noise or dataset-specific artifacts. My project explores multiple modeling versions across two main tasks, like I said, classification and segmentation. For classification, I evaluated both baseline and modern CNN architectures. The baseline includes custom CNNs and VGG networks, which serves as a reference point for performance. More advanced models include ResNet, which introduces residual connections to improve rate and flow. EfficientNet, which scales depth, width, and resolution efficiently. ConvNeXt, a modernized CNN inspired by transformer design principle. For segmentation, the pipeline begins with segment anything model, or SAM, which is used to generate initial tumor maps automatically. These maps are then refined using fully supervised architectures such as UNet and Deep Lab V3+, which are widely adopted in biomedical image segmentation. This multimodal approach allows for a systematic comparison and highlights trade-offs between complexity, accuracy, and interpretability. My architectures used in this project span multiple generations of convolutional neural networks, or CNN. For classification, VGG models use deep stacks of convolutional layers with small kernels, offering strong feature extraction but high parameter counts. ResNet improves upon this by introducing skip connections, allowing deeper networks to train effectively without vanishing gradients. EfficientNet introduces a principal compound scaling strategy, achieving strong accuracy with fewer parameters and better computational efficiency. ConvNeXt modernizes CNN design by adopting transformer-inspired elements while retaining convolutional inductive biases. For segmentation, UNet employs an encoder-decoder architecture with skip connections that preserve spatial resolution. Deep Lab V3+ further enhances segmentation through address spatial pyramid pooling, enabling multi-scale contextual understanding. Together, these architectures cover both classical and state-of-the-art design paradigms. All models were implemented using TensorFlow and Keras, enabling rapid experimentation and reproducibility. Training was conducted on GPU resources available through Google Colab, which constrained batch size and epoch count but reflected realistic research conditions. Optimizers such as ADAM, RMS prop, and SGD with momentum were evaluated depending on model architecture and convergence behavior. Learning rates were carefully tuned, typically ranging from very small to small learning rates, with early stopping to prevent overfitting. Regularization techniques such as dropout L2 weight decay and data augmentation were essential due to the small dataset as I mentioned earlier. For segmentation models, loss functions such as dice loss and combined cross entropy plus dice loss were used to emphasize overlap quality. Overall, training focused on stability, generalization, and interpretability rather than raw accuracy alone. Evaluation strategies differ significantly between classification and segmentation tasks. For classification, standard metrics such as accuracy, precision, recall, F1 score, and ROC AUC were used. Given class imbalance, particular attention was paid to recall and false negatives. Confusion matrices provided insight into error types, especially cases where tumors were missed. For segmentation, evaluation focuses on spatial overlap rather than simple correctness. Metrics such as dice coefficient and intersection over union, or IOU, quantify how well predicted masks align with ground truth. Pixel accuracy alone is insufficient, as it can be misleading when background pixels dominate. Visual inspection of segmentation overlays were also used as a qualitative evaluation method, which is especially important in medical image contexts. This multi-metric approach ensures a balanced and clinical meaningful evaluation. When comparing models, clear trade-offs emerge between complexity, accuracy, and interpretability. VGT models provided a strong baseline, but were computationally heavy and prone to overfitting. ResNet models improve robustness and convergence, particularly on augmented data. EfficientNet achieved comparative accuracy with fewer parameters, making it attractive for deployment-oriented scenarios. ConvNeXt demonstrated strong representational power, particularly in challenging cases with subtle tumor features. For segmentation, UNet consistently produced reliable masks, while DeepLab Plus excelled at capturing complex boundaries. On the held-out testset, performance differences between models became more apparent. Classification results showed that retrained architectures significantly outperformed custom CNNs, particularly in recall. Some models achieve high accuracy but suffer from false negatives, which are especially critically important in medical applications. For segmentation, DICE and IOU scores revealed that DeepLab V3 Plus generally produce smoother and more complete tumor masks. However, UNet demonstrated greater stability across different image qualities. These results emphasize the importance of evaluating models on unseen data and interpreting metrics in a clinical context. Visualization provides essential insight beyond numerical metrics. For classification, RADCAM heat maps show where models focus attention when predicting a tumor presence. These maps often align with tumor regions, increasing interpretability. For segmentation, overlaying predicted masks on MRI images allow direct comparison with ground truth. In many cases, models successfully captured tumor boundaries, while errors often occurred at fuzzy or low contrast edges. These visual results reinforce quantitative findings and help identify systematic failure modes. Visualization is especially important in medical AI, where trust and transparency are critical for adoption. Here, I illustrate a conceptual demo of the pipeline. An input MRI image is first passed through the classification model and as well as the segmentation model to determine whether a tumor is present. If detected, the image proceeds to the segmentation stage, where the tumor region is localized and highlighted. The output includes both the binary prediction and a spatial mask, providing interpretable results. While this demo is offline, it demonstrates how such a system could be integrated into clinical workflows as a decision support tool. The pipeline is modular, allowing individual components to be improved or replaced independently. Several insights emerged from my project. First, data quality and preprocessing had a major impact on performance, often more than architectural changes. Second, pre-trained models consistently outperform models trained from scratch, even with aggressive augmentation. Third, segmentation quality is highly sensitive to contrast and boundary clarity. Finally, quantitative metrics must be interpreted alongside qualitative inspection to avoid misleading conclusions. These insights reinforce best practices in applied medical machine learning. Several aspects of my project worked particularly well. Transfer learning significantly improved convergence and generalization. Mystical contrast enhancement improved tumor visibility. UNet and Deep Lab V3 Plus produce clinically meaningful segmentation results. Likewise, ConvNeXt based the second model of classification. However, challenges remain. The dataset size limited generalization, and some generated masks were sometimes inconsistent. Class imbalance also complicated evaluation and required careful metric selection. These limitations point to clear directions for improvement. My project reinforced several key lessons. Preprocessing is not optional in medical imaging. It is foundational. Transfer learning is essential when data is limited. Evaluation matrix must align with real-world consequences. Finally, interpretability is just as important as accuracy. These lessons extend beyond my project and apply broadly to apply AI in healthcare. My future work might focus on scaling and realism. Incorporating larger datasets such as breast would improve robustness. Extending to 3D CNNs would enable volumetric tumor analysis. Ensemble models could improve reliability. Finally, clinical collaboration would be essential for real-world validation. This enhancement would move the project closer to deployment-ready systems. In summary, my project developed a comprehensive deep learning pipeline for brain tumor detection and segmentation. By combining classification and segmentation models, it reflects real diagnostic workflows. Modern CNN architectures demonstrated strong performance, even under data constraints. The results highlight both the promise and challenges of medical computer vision. This is the end of my presentation. Thank you for your attention. I welcome any questions.